Machine learning is used more and more in real-life situations. Therefore, it's crucial to thoroughly evaluate these models, making sure they work accurately and efficiently. One method that has shown a lot of promise is data slice finding. It tests the model's performance at specific data subsets, allowing us to understand how the model works under different scenarios. However, data slice finding still faces some challenges. It can be expensive and time-consuming to get the metadata you need to calculate the slices. Furthermore, it takes a lot of time and effort to figure out the root cause for the data slices problems with current methods. These challenges are particularly difficult for vision tasks, where the data is unstructured and don't always contain metadata. We propose AttributionScanner, a visual analytics solution to validate image classification models. Without relying on metadata, our tool generates interpretable data slices that can be explored in our system, facilitating the discovery of model insights. Our method uses GradCAM to create interpretable data slices, which provide insights into the model failure cases. Our framework also summarizes the data slices for easy understanding and allows model iteration, closing the loop in the ML development cycle. Our data slicing approach leverages GradCAM to extract a weighted feature vector, which captures the most crucial image features for a model's prediction. Next, we cluster the weighted feature vectors, creating data slices that are easy to understand by data scientists. Exploring data slices one image at a time is very time-consuming. To facilitate this process, we invent the data slice mosaic visualization that captures the main patterns contributing to a model prediction. For each data slice, this approach summarizes the feature attribution within the slice via feature visualization. With our system, the user can easily identify and annotate spurious correlations in the data and annotate them with a few clicks. This annotation is automatically propagated to all slices. For example, consider a hair color classification model. If the most discriminative feature is the mouth, the model is focusing on the wrong portions of the image, creating spurious correlations. The spurious slices can then be mitigated by retraining the neural network using a core risk minimization approach, which adds noise to the spurious features based on the data slices. Our interface consists of three main parts. In the slice table, we allow users to explore and rank the data slices based on slice metrics. The slice mosaic view shows a visual summary of the data slices. Finally, the slice detail view displays the individual images and attributions from the selected data slice. Let's see how our system can be used to understand and mitigate model issues. As a first example, let's investigate a model for hair color classification. We trained a model to predict gray hair in images from the Celeb dataset, obtaining a validation accuracy of 98.03%. After the user imports the validation dataset and the trained model into our system, it automatically computes the data slices and slice summaries. We notice that the worst data slice, slice 44, has an accuracy of 0.72. When we inspect detail view, we see that it corresponds to images where the model focuses on the background. We conclude that background is a spurious attribute. Let's now look at an example of problems in high-performing slices. A hair color classification model should focus on the hair features. This is the case on the data slices clustered on the left. However, we see that many slices with high accuracy do not focus on hair, but instead their attribution is on the mouth and eyes. With a few annotations, we can use the core risk minimization approach to mitigate these spurious correlations and improve model performance. The pixel attributions of the new model are in the hair region, as expected. As a second example, we look at a model that classify birds as either water birds or land birds. The model obtained an accuracy of 85.74%. We begin by looking at the worst performing data slice. We can see that the model is using water backgrounds to classify birds as water birds. As we move on to other underperforming slices, we see that a similar error occurs. In this case, the model is classifying land birds based on a land background. We confirm this insight using the confusion matrix view. After we annotate a few slices, AttributionScanner automatically propagates these labels to the other slices. Finally, when we retrain the model with the core risk minimization, we see that the new model is more accurate and reliable, as it uses the correct features to make the classification. In conclusion, AttributionScanner is a novel, metadata-free visual analytics approach for data slice finding and model validation. A core component of our approach is the slice mosaic view, which can quickly summarize and help users to identify data slice problems. Our workflow enables users to fix model mistakes with just a few interactions.